Hello, Monica. This is Thaisa. How are you?
Hi, Thaisa. Nice to see you.
Nice to see you too. Yeah. Use this opportunity to learn about more about your job, your work.
Okay, thank you. Yeah. Yeah, lots of overlap, but I'm mostly going to talk about simulations today. But
okay, yeah, yeah, it's a good opportunity for me to to learn it. Yeah.
Welcome also, Thaisa. Thank you for joining us.
Okay,
it's great to have you here.
Thank you.
Okay, so I think we should get started. Hello, everyone, and welcome to another talk in our webinar series. This webinar is also being streamed live on YouTube. You can find a link on our website or access it on our YouTube channel. That's Linea MCTI. Today, we have the honor of having Dr. Monica Valluri, a research professor from the University of Michigan. Dr. Valluri uses numerical calculations and simulations to probe the observed galactic phenomena in order to understand the physical processes that produce them. Her current focus areas are supermassive black holes and the interactions between dark matter and luminous matter in galaxies. Her work on black holes has allowed her to explain how they affect the properties of their host galaxies and to generate more accurate mass measurements for them. Over the past decade, she has focused on the effects of supermassive black holes on the stellar bores of disk galaxies. Dr. Valluri, thank you so much for being so kind and having accepted to give us a webinar talk today on such an interesting topic. The floor is yours.
Thank you. Thank you so much for the invitation. It's a great pleasure for me to be here today online. I know that there's a lot of interest in galaxies and cosmology in Brazil, and I'm excited to be able to share my work with you. So I would like to start by introducing my collaborators. Vance Wheeler is now a PhD student at the University of Chicago. Shashank Dattatreya is now a PhD student at Yale. Both of them did this work as undergraduates or post-baccalaureates. Leandro Beraldo y Silva is now postdoc here at the University of Michigan, and he got his PhD in Brazil and was also postdoc at the University of Central Lancashire. Eugene Vasiliev and Victor De Batista are also longtime collaborators. So the goal of this talk is to tell you about supermassive black holes and their effects on barred galaxies. So it's been one of the most important discoveries from in the last 20 odd years has been the observation that supermassive black holes have masses which are very tightly correlated with the properties of their host galaxies. One of the strongest correlations is the one between black hole mass and velocity dispersion, called the M-sigma relation, and was discovered simultaneously by Ferraresi and Merritt and Gebhardt in 2001. It is now well understood. So this plot here, which is from a paper by McConnell and Ma, shows galaxies of different morphological types. The green ones are brightest cluster galaxies. The brightest cluster galaxies. There are elliptical galaxies and spiral galaxies, and the late type galaxies. And one of the things that is clear from the work that has happened over the past 2 decades is that early type galaxies tend to have somewhat more massive black holes than the late type galaxies, and the velocity dispersions in late type galaxies for a given velocity dispersion, the black hole masses are about a factor of 2 smaller in late type galaxies. Now, there is still a great deal of uncertainty about what causes these scaling relations. It is unclear whether the black holes just grow in sync with their host galaxies through tightly regulated feedback, or perhaps it's just the averaging of galaxy properties due to hierarchical mergers. And both hierarchical mergers and feedback are definitely very important at the high mass end. At the low mass end, where black holes are much less massive and tend to reside in late type galaxies or late type spiral galaxies, it is thought that secular evolution, which means the effects of spirals and bars on the galaxy, on black hole growth, might be important. But how this affects galaxies is unknown. So to just step back for a moment, most disk galaxies have bars. And a bar is a central elongated stellar structure which rotates coherently at the center with what's called figure rotation. When a barred galaxy is viewed edge on, it often has a structure which looks like a peanut or a box-shaped bulge. And these are thought to form from what's called a buckling instability, but it's still not entirely known what causes this boxy peanut. The angular rotation frequency of the bar, or the pattern speed, depends on the type of bar, but bars tend to be found within the radius where this pattern speed is within the rotation frequency of the stars in the galaxy. In that elongated structure, if you're in the frame of the bar, the stars are actually moving on orbits which tend to be aligned with the bar. And this is an example of some of the various kinds of orbits that occur in barred galaxies. And so although the entire bar is moving in the frame of the bar, stars tend to oscillate back and forth along the bar. The bar fraction is known to change with redshift. In the local universe, it's about 65%, and then it drops to about 20% by redshift of 0.85. Bars are really have been long considered to be important because they are non-axisymmetric and therefore can transport angular momentum. And this transport of angular momentum is crucial for allowing gas to feed the black hole. But there have been really very little understanding of exactly how this can happen. And as I will show, for a very long time, for nearly 30 years, it's been believed that actually black holes might destroy bars rather than help them. There's also observations that bars might be offset from the M-sigma relationship for early type galaxies. So if you look at elliptical galaxies, lenticular galaxies, the spirals with bars tend to be offset from the M-sigma relationship for these other galaxies. And the barred galaxies could have sigmas between about 15 to 40% larger than the sigmas for elliptical galaxies with the same black hole mass. It is still unclear whether although there is some controversy about this result, studies which have carefully looked at classical bulges and what are called classical bulges, which are thought to form via mergers, versus pseudo bulges, which are thought to form via secular evolution, suggest that classical bulges largely are aligned with the elliptical galaxies, whereas pseudo bulges are offset by maybe even a factor of 6. And so this is suggestive of the fact that there is something happening in barred galaxies which is different from what's happening via mergers, or secular evolution may play a role which is different from mergers. There are also several papers which suggest that there is no difference between barred and unbarred galaxies when you look at galaxies with AGNs. So in these AGN samples, black holes are measured in different ways. So they're measured normally using reverberation mapping or a single time measurement of the H beta line. And so in such galaxies, there is apparently very little difference or no difference between barred and unbarred galaxies. And this suggests that, in fact, it might be the black hole mass measurements in quiescent galaxies that is responsible for some of these offsets. And so that is that is an important issue to investigate. Another reason why it's important to look at AGN black holes in disk galaxies is that observations of AGN in the local universe suggest that the majority of high luminosity AGN actually live in disk galaxies and not in elliptical galaxies. And so in if you look at Seyfert galaxies, about a really small fraction of them lie in ellipticals compared to barred galaxies with pseudo bulges. And since redshift of 2, it is known that a significant fraction of black hole growth is actually occurring in disks. And so one of the goals of this talk is to revisit a question that has been around for a long time, and that is, how do black holes affect barred galaxies? So there is work which goes back to 1988 from Norman and Hassan, and has repeatedly found, including model simulations with gas done by Du, De Battista et al. In 2017, that if you grow a black hole inside a bar, it weakens or destroys the bar. Now, in order to destroy the bar completely, you need a really massive black hole of about 2 to 5% of the disk mass. And so that is an unrealistically large black hole. But for realistic black hole masses of about, say, 0.2% of the disk mass, the black hole is found to weaken the bar and reduce the bar strength. So this suggests that people have argued that this suggests that black holes and bars don't really have that much to do with each other. If a black hole destroys a bar, then it must limit how much the bar is able to feed the black hole. However, if you look at the black hole fraction in active galaxies, you notice that there's actually quite a striking agreement. That is, although the error bars are large, it does seem like the fraction of AGN is slightly higher, very slightly, but slightly higher in galaxies with bars than in inactive galaxies. And so the question, and also black holes clearly seem to grow at earlier times than bars. As I said, bars tend to form at redshifts about the bar fraction at 0.8 is about 20%. So we don't know what it is at higher redshifts because it's hard to actually detect bars. But we know that black holes exist all the way to much higher redshifts of 6. We see dozens of hundreds of quasars. And so black holes already exist in disk galaxies. And so what is the effect that these black holes have on the bars if they form either earlier or alongside the formation of the bar? So there are 2 goals to this talk, or well, 3. The first is to understand how black hole mass measurement from stellar dynamical methods can be improved in bars, and whether or not there are problems with the current measurements of black hole masses in barred galaxies. And the second is to try and understand how this coeval formation of black holes and bars affects the bars. Do black holes actually destroy bars, as has been claimed in the past? And then I'll just, in the last few minutes, I hopefully will have time to give you a quick preview of 2 projects which I'm associated with to measure black hole masses with JWST, and hopefully this will give us a new ways to understand black holes' growth in the universe. So, sorry. Okay, so there are multiple. I don't know why my computer is very slow to respond for some reason. Okay, so there are many ways for measuring black hole masses in the universe, but primarily the overall idea is that the black hole dominates the gravitational potential inside some radius, which we call the sphere of influence or the radius of influence. And this radius is actually very small in most cases. And so we need very high spatial resolution observations. Black hole masses have been measured using gas dynamics, using maser emission from nuclear disks. But the predominant method for directly measuring black hole masses is by what's called using stellar dynamics, either what's called Jeans modeling or Schwarzschild modeling or orbit superposition. And this method has been responsible for, as I said, the majority of black hole mass measurements in galaxies. And so the way this works is that you start with a galaxy, you start with an image of a galaxy, you deproject its light distribution to estimate the stellar potential, you assume some additional dark matter potential, a black hole, a variety of different black hole masses, an inclination angle for the galaxy, a mass to light ratio for the stars. And this gives, for each choice of these model parameters, you have a galaxy potential in which you construct a large library of orbits, which you then project project to get both the spatial distribution and the kinematics. And then you weight these different orbits in order to produce the target density distribution and the target kinematics. And so you do this for a large number of parameters, and the best fit inferred black hole mass to light ratio, inclination, etc., give you the estimated black hole mass with the uncertainties. It is important to note that although something like over half of the black holes which have been measured using this method are in disk galaxies, all of them assume that the galaxy is axisymmetric. Every single one of them makes this assumption that the galaxy is axisymmetric, even though we know that about 2/3 of disk galaxies contain bars. And in fact, it is, I would say that about for 25 of the 80 something galaxies with stellar dynamical black hole mass measurements have been measured, have bars. So we did a test where we used an axisymmetric code. This is a code which I wrote back in the early 2000s, which I call MassMod. It assumes the galaxy is axisymmetric. It does this whole Schwarzschild modeling method, but we applied it to 12 mock galaxies generated from n-body simulations with which had bars, and we varied the inclination of the disk, we varied the position angle of the bar, and obtained the best fit black hole mass both for all these barred galaxies as well as for an axisymmetric control galaxy model which our axisymmetric code was designed. And the result is shown here. So as I said, in all these mock galaxies, they had just exactly the same true black hole mass, which is given by this dotted line. If the galaxy was assumed to be edge-on and axisymmetric, the code recovered. So that's this blue curve here. These are chi-squared, delta chi-squared contours. The code recovered the true black hole mass. In the case where you had bars, if the galaxy was edge on, so that is this purple line and this dark blue line, if the galaxy was edge on, regardless of the position angle of the bar, the black hole mass was actually fairly well recovered. But when the disk begins to be inclined, that is, so inclination of 45 degrees or 20 degrees, you see that the recovered black hole mass is now, about 2.5 times larger, or even 6.5 times larger for nearly face-on galaxies. And so this suggests that ignoring the presence of a bar when modeling it with an axisymmetric code is really disastrous. It could result in very wrong measurements of black hole mass. So, there is. What we did. What is the reason for this? I mean, so it's important to understand why this is happening. So there is a well-known problem in mass determination called the mass anisotropy degeneracy. You can have stars in a galaxy which are primarily tangential, and we define a parameter called beta, which is 1 minus the velocity dispersion in the tangential over the velocity dispersion in the radial direction. These tangential orbits produce velocity profiles, which are either double peaked or flat topped like this, and they have a negative kurtosis, or what's called a negative H4 Gauss-Hermite coefficient. And radial orbits have much more, have what are called, have beta greater than 0. They're radially anisotropic, and they have these peaky line of sight velocity profiles. Now, if you have a galaxy where you don't know whether stars are radial or whether they are tangential, and you just measure the velocity dispersion, you may estimate a higher black hole mass if you just assume that the stars are isotropic than you would if you assume that they're radial, but they're actually tangential. And so this is an image. This is an image taken from a paper by Michele Capellari, which shows kinematics for an axisymmetric disk galaxy. So you see that the velocity shows the usual, the positive and negative velocities. Velocity dispersion peaks at the center. H4 is this quantity which tells you whether the line of sight velocity distribution is peaked or flat topped. And so it tends to be peaky at the center and then go down at larger radii. In a barred galaxy, you see certain features. So this is the position angle of the bar, and you see that the velocity field is kind of twisted. So you see that. You also see that the velocity dispersion contours are sort of twisted relative to the position angle of bar. And most importantly, you see that there is this region here with negative H4. So as this is a disk which is about 45 degrees, but this shows up for face-on disks as well. You see this region here with negative H4. Now, this negative H4 is in an axisymmetric galaxy, as I said, implies that in an axisymmetric galaxies, negative H4 assumes that implies that stars are on tangential orbits. But when in the case of a bar, I said that all the stars in the bar are actually streaming along the bar. And the reason you see a negative H4 is that the whole bar is rotating, right? So if you model this galaxy with an axisymmetric code, then the code wants to put tangential orbits on the in this barred region. Just it assumes that there are tangential, that these negative H4 comes from tangential orbits. Now, if the galaxy is most close to face-on, those tangential orbits don't actually contribute very much to the line of sight velocity dispersion. So in order to increase the sigma, so the sigma is still quite high, to increase the sigma, you need to raise the black hole mass. And so this is why the black hole masses can be overestimated in barred galaxies. How severe is this problem? As I said, about 23 of the 85 galaxies with stellar dynamical black hole mass measurements are barred, and many of them are at the low end of the black hole mass, function, where the sphere of influence is poorly resolved, and so this is a problem for a fairly large number of galaxies. With Eugene Vasilyev, we developed a new code called FORSTAND, which stands for Flexible Orbit Superposition Toolbox, and it is part of what's called the AGAMA Dynamical Modeling Toolbox. It is applicable to any kind of galaxy, not just bars, spherical, axisymmetric, triaxial, highly flattened. The density distribution is discretized in a basis function. It can deal with all different kinds of data, and it is extremely fast. I mean, compared to my code MassMod, which would take several months to do a set of models, this can do dozens of models in a few hours, and is extremely efficient for and it's a and I'd also like to emphasize this code is publicly available to anybody who wants to use it, and there are training sort of tutorials on how to use it as well. We applied this code to an n-body, mock data for an n-body bar, and we found that you can recover the bar pattern speed to within 10%, which is actually something that can't be done with any other code for any orientation. So this was one of the unintended consequences of this. We were really going to try to measure black hole masses, but turned out that we can also measure bar pattern speeds extremely accurately. One of the new developments that we have, which was led by my student Shashank, is to deproject this boxy peanut shape. So this image shows you what the boxy peanut shapes are like, and we now characterize that boxy peanut shape using a ugly and complicated function. But basically, there are two main parameters. There is this R peanut, which tells you how far apart the two peanut lobes are, and an H peanut, which tells you how high above the disk this peanut is. And this three-dimensional density distribution is added to an existing code called IMFit, which is used for fitting surface density fitting of observational galaxies, and it allows us to measure. This is an example of a three-dimensional n-body snapshot, and this is the recovered density distribution from this deprojection code. It is able to fit the surface brightness to better than 15%. It fits the three-dimensional mass density everywhere better than 7%, and the gravitational potential is fit better than 2% in the entire, at all places in the disk on average. And so we're able to recover the pattern speed with this analytic density model to better than 10%, and black hole mass between 10 and 15%. So this is a significant improvement to our ability to measure black hole masses in galaxies. So so just to summarize this part of the talk, black hole masses are overestimated when you measure them with axisymmetric models. And this could be in part one of the reasons for the observed scatter in the M-sigma relation at the low black hole mass end. But with this new code FORSTAND and our new bar deprojection algorithm or our new bar deprojection module added to IMFIT, we're able to recover black hole masses extremely well. So I'm going to now switch tracks and go on to the next topic, which is looking at the effect of black hole growth, coeval black hole growth on bars. And just to summarize, we said that black holes start to grow at higher redshifts than bars. We already know that there are black holes at redshifts of 6 or higher. Most black hole growth is thought to have occurred before a redshift of 4, just based on the quasar luminosity function. And so we know that even in disk galaxies, there are probably some form of slightly early seed black hole in most galaxies. And since bars actually form much later, it is really important to look at what early growing black holes do to bars. So we carried out a series of simulations. These were simulations which were really conducted by Vance Wheeler using a code called Galaxy, which was written by Jerry Selwood. So we basically we ran a number of different simulations, but the disk galaxies had parameters similar to the Milky Way, standard exponential disk with a live dark matter halo, over 10 to the 7 particles in total. We ran a control model which doesn't have a black hole, so we just let that disk evolve and it forms a bar, and we studied the evolution of that bar. And then in another series of simulations, we have a black hole which has a mass of about 7.6 times 10 to the 7 solar masses, or about 2% of the bulge mass. And the only thing that is varied is when the black hole starts to grow. They all grow at the same rate over about 50 dynamical times, but which is about 800 mega years, but they start at different times. So this plot shows a summary of the effects of this black hole growth. So the quantity on the y-axis is the bar amplitude. Initially, it sort of rises, and this is due to, it's actually the m equal to 2 mode amplitude. So it's the amplitude of all things which have, a bifold symmetry. And so the initial peak is due to the spiral, but then this growth is due to the growth of the bar. The strong bars, and so you notice that all of these things go, the bar strength increases and then it drops in all these cases. And this is because bars generally go through a phase called buckling. And buckling is a process where the bar flexes out of the plane of the disk, suddenly reducing the bar amplitude and vertically heating the disk. And the simulations are as follows. So this blue curve here corresponds to our control model with no black hole. The orange curve has a black hole which starts at the graph at the very start. So this is this orange bar here tells you the time over which the black hole grows. There are 3 models where the black hole grows before the bar buckles, but after the bar has started to form. And then there's a model just to compare with all the previous simulations. So as I said, 30 years of simulations from Hassan and Norman all the way to Du et al. In 2017 grew a black hole in the bar after the bar had buckled. So this brown curve here at the bottom shows you what happens to the bar if the black hole is introduced at the end. And so one of the important things you notice here, just from this, is that when a black hole grows early, the bar strength is higher and keeps growing. When the black hole grows after the bar buckles, it weakens the bar. Right? So it weakens the bar. This is consistent with previous results. So we can summarize this in this way. We can compare the bar strength in all our different models with the bar strength in the control model. And so as a fractional difference. So the control model is given here. And the time axis here is the time at which a black hole is introduced relative to when the bar buckles in this control model. And so you see very clearly that the earlier a black hole is introduced, the greater the bar strength. And the only case in which the black hole weakens the bar is the case where the black hole is grown after the bar is formed. Okay, so this is the main result I want you to take away from this. So to understand what is causing this, it's somewhat helpful to understand what's called this buckling instability. So bars, as I said, have stars which are moving along these elongated orbits. This is just a cartoon. And when this happens, the velocity dispersion in the radial direction increases significantly compared to the velocity dispersion in the vertical direction perpendicular to the disk. And so small perturbation out of the plane of the disk can cause stars to stream across this curve, and that results in an increase in the sort of the centripetal force as stars are streaming across this curve, causing the bar to buckle. And this is observed in simulations. The calculations of this bending or bar buckling go back to Tumre in 1967. And for an infinite sheet, he showed that if you have a bar's velocity dispersion in the vertical direction over the radial direction of greater than 0.3, it stabilizes the bar against buckling. But we find that in other simulations, Merritt and Selwood found that for finite bars, bars were stabilized against buckling when this velocity dispersion was greater than 0.6. And in all these cases, when this bar buckles, it heats the disk, redistributing the kinetic energy in the radial direction with the vertical direction. Okay, so if you look at the buckling amplitude that is defined as so, we find that this lower plot gives the buckling amplitude. We find that in all cases where the black hole is grown earlier than before buckling, the buckling is either weakened, so this amplitude, for instance, is lower than this, or it is delayed, or it's both. So buckling is significantly altered by the presence of the black hole. And the reason this happens turns out to be this condition on the velocity dispersion in the vertical direction versus the radial direction. So this is the control model, and it shows radius along this axis, time along this axis, and the color shows the velocity dispersion. This is the velocity dispersion in the radial direction, this is vertical direction, and this is their ratio. And the vertical line shows when the bar buckles, and you see that when the bar buckles, this ratio jumps, right? So that's what buckling does. It increases the vertical velocity dispersion. It causes this ratio to jump. In the case where you have a black hole introduced early, you notice that actually there is an increase in the velocity dispersion much earlier. Vertical velocity dispersion increases much earlier. So there is in this the vertical velocity dispersion. So this is it's hard to see on this curve, but it's 0.6, and you see that the bar is actually beginning to be stabilized even before it does eventually buckle, but it buckles later because of the fact that the black hole is actually causing an increase in velocity dispersion in the center. Okay? So we see that the black hole also causes the peanut strength to increase. You can see this visually here. This is the case without a black hole. This is the case with the early growing black hole. This peanut shape is extremely strong. if we use Shashank's way to characterize the peanut strength using those quantities I described, R peanut and H peanut, you see again a correlation that the peanut is stronger in the case of when the black hole forms first and when the forms before the bar, but it's weaker when it is, or when it forms after bar buckling. So this, there are, so the paper, which we'll hopefully submit in the next few weeks, goes into a significant amount of detail using something called frequency analysis and understanding resonances in the orbits. But that's a little too much detail for this talk. So I'll just summarize our understanding of why this happens by saying that these boxy peanut shapes here are the result of many different types of resonant orbits in the bar. And if a bar is formed without a black hole, there are different families of orbits which are populated than when the bar forms around a black hole or when the bar forms along with the black hole. And so we see that this is a model with the black hole. And these are different types of orbits. They're just listed. You don't need to pay attention to what they are. But the families in the case with the black hole are actually quite different from the families of orbits which are formed without a black hole. And the reason the late growing black hole weakens the bar is that there are a lot of orbits which pass through close to the center, and those orbits are scattered by a black hole if it is introduced late. But if it is introduced early, then those orbits actually never exist. They are populated. The bar is populated by different types of orbits, and those orbits actually end up strengthening the bar. And so the increase in velocity dispersion, there is some work from Hartman et al., which I talked about earlier, which shows that the increase in velocity dispersion relative to an unbarred galaxy is proportional to the bar strength. And since we find that the bar strength increases depending on how early a black hole was introduced, you can see that the strongest bars have the highest velocity dispersion. And this we find is also correlated with the fact that the stronger the bar, the greater its ability to transport material inwards. So there's a mass excess in the inner region, stellar mass excess, which deepens the potential, but it can also increase the inflow of gas, which can feed the black hole. Okay, so if we want to go back to our M sigma relation, we'll see that a coeval or early growing black holes can actually cause, all our simulations had the same black hole mass, but the strength of the bar was different and the velocity dispersion increase that it produces is different. And so it causes a larger scatter. And so it's possible to understand the fact that there's greater scatter in late type galaxies from just the fact that there is this difference between how secular evolution affects velocity dispersion. What's also interesting is that because there is this correlation between when a black hole was introduced and the strength of the bar, it suggests that you could actually use the physical characteristics of the peanut to maybe infer something about when a black hole formed in a barred galaxy. So in the last few minutes, I'm not going to try not to take too long, just another couple of minutes. I just want to advertise that there are two programs which I'm involved with to measure black hole masses in galaxies. The first is led by Misty Benz and is to observe this Seifert 1 galaxy, NGC 4151, one of the nearest active galaxies, which is known to have a black hole mass between 3 and 5 times 10 to the 7 solar masses. So we're observing it with NIRSpec to get stellar kinematics, and we will use our FORSTAN code to measure the black hole mass. There's also a cycle 1 proposal to study 18 compact elliptical galaxies in the Virgo cluster and try to measure black hole masses in these systems. This is a project is led by Matt Taylor at the University of Calgary. And we will be, we hopefully will start getting data by the end of December. And the reason that JWST is likely to revolutionize black hole mass measurement is if you compare with, say, NIFS, the near infrared spectrographs on Gemini, it has, say a pixel size of, 0.04. So, you can rebin this to about 0.05 arc seconds spatial resolution, but it has the PSF has this very broad core halo structure, which makes it difficult to resolve the central region of the black hole. In contrast, the NIRSpec IFU on JWST is dithered to 0.025 arc second, so it will allow us to get higher spatial resolution. It has a lower spectral resolution, but because it's in space and because the sky is has lower background in the infrared, it is a much more sensitive instrument, and so we can obtain the same signal to noise of 50 in a 1.5 hour exposure compared to a 5 hour exposure, an 8 hour exposure on Gemini. We hope that the lower spectral resolution will not affect our ability to measure the Gauss-Hermite coefficients, but this is likely. So we are optimistic that JWST will really revolutionize black hole mass measurement. So I'm going to just leave up my my summary. I have a key figure to remind you of what my key results are, and I will stop here and take questions.
Thank you so much, Dr. Valluri, for the very interesting talk. Now we have time for questions from the audience. You can either raise your hand or maybe post them in the chat. Thaisa, do you have your hand up?
Yeah, I raised it presently. Hi, Monica, very nice talk, thanks. Thank you very much. I have a question. For example, as far as I understand, the black holes formed more or less together with galaxies back in the early universe, because we see quasars almost as far as galaxies, right? The redshifts are almost the same. Maybe galaxies a bit larger. But so I believe that this is saying that that maybe the black holes are formed before the galaxies, don't you think? Or you're so if the black holes are formed before the galaxies, before the bars, then it's always helping to increase the strength of the bar, as far as I understood from your talk. But so far there is some little difference. The newest observations, you say, show a little bit of an excess of bars in AGN, not much, but a little bit. So I don't know if you want to comment on that. Because I don't know if you would like to say that if the black hole grows a lot after the bar, is this or always it is formed after the bar? You had to be formed, or you can grow also?
Yeah, I think that I think that part of the reason that there is only a slight difference between the fraction of AGN in barred versus unbarred galaxies is that typically when a bar forms, it lives forever. It really doesn't get destroyed, at least based on our analysis that really doesn't, black holes, if they form early, and I think you're right, I think they form early. Most of them are formed at very high redshifts, and then maybe the disks actually form around them. So I think that most massive disks probably have a pre-existing black hole. So the bar, if once it forms, is not destroyed because it forms around this black hole. But the AGN is only active for a short time, right? So AGN life's duty cycles are really quite short, so they can turn on and turn off. And so I think the fact that there isn't a correlation is to me is less indicative of the fact that a bar is not feeding the black hole. And I think the kind of work that you're doing, where you're observing gas and galactic nuclei and looking at non-axisymmetric feeding, that is really crucial to, and I'm hoping we can do more of these barred galaxies precisely to understand the role of bar feeding in the local universe and at higher redshift. But I think that for a long time, people have assumed that nuclear bars, which were thought to be important for forming black holes, would be destroyed by the black hole. And I don't think that's true. I think that it's only destroyed because you put in the black hole after the nuclear bar is formed. If you have a black hole and allow the disk to become bar unstable, the bar adapts. It's quite, there are lots of orbits that can support a bar. And so I think that we have to go back and revisit those, the issue of, say, nuclear bars and feeding, because I don't think the standard wisdom is that they can't be useful, or at least they're not as useful as you'd like. But I think that that's not true.
Okay, thank you.
Thank you. We have time for more questions. If you want, you can put your hand up, or if you want, either virtually or in the camera, and I'll call. Okay, Monica, while we wait for people to find their hand up button, I have a question. Sure. Can you please go back to the slide that says deprojecting the boxy peanut bulge? It's way in the beginning. I think it's from your first part of the talk.
Yeah. Sorry. Yeah.
Yes, this one. Right. So can you maybe I just didn't understand this, but so for each of these images, there's like the peanut one, and then underneath there's an image of a bulge. Can you explain that, please?
Yeah. So sorry, I should have been explained this more clearly. So this is of course the face-on image. This is the image of the disk when you observe it, the disk edge on, when the bar is perpendicular to your line of sight, and the bottom panel is when the bar is along your line of sight. So when you see the bar along your line of sight, it looks like a bulge, even though there is actually a bar there. So, but it's still an edge-on disk with the bar aligned along your line of sight.
Okay, so it's the same galaxy, just how you're seeing them differently.
Yeah, just along three different axes.
Okay, thank you. I thought it was a different one. Thanks for explaining.
Okay.
Do we have more questions from the audience?
I have one more question.
Yes,
as Monica mentioned that you mentioned we are talking about large-scale bars, but you mentioned also nuclear bars. I believe they are different, or don't you? Or do they behave? Because I have this idea that maybe nuclear bars that are, say, within 1 kiloparsec are more linked to the growth of the black hole, and they can be destroyed more easily. Do you agree with that or no?
So I mean, my honest answer is I don't know because we haven't done the simulations.
Okay.
But I've looked at the simulations which have been done with nuclear bars and black holes, and in all cases, the black hole is grown after the nuclear bar forms. And so I suspect that the destruction is less. I'm not sure that there will be necessarily destruction because I don't think there is a reason why the nuclear bar should behave differently from the large scale bar, at least in terms of the orbits that support it.
Okay.
But I don't know. That's a question that we look to investigate further. And you know, also with simulations which include gas, because I don't think I specified, but these simulations were all with just n-body simulations.
Okay. Yeah. So maybe the nuclear bars are more gas rich, maybe.
Yeah.
Okay. Thank you.
Sorry, just for clarification, can you explain again what the nuclear bar is?
Oh, so so nuclear bars are, sort of again stellar bars, sometimes seen also with in gas, but are found typically within a kiloparsec or even smaller of the galactic center, whereas these, what I've been talking about mostly are what we call large scale bars, which can extend out to 4 or 5 kiloparsec. In some simulations, these nuclear bars actually have a different pattern speed from the large scale bar. They can sort of have and so there are interesting effects, resonant effects between the oscillation of the nuclear bar and the large scale bar, but I haven't, we haven't simulated those in this work yet.
Thank you, Monica. I'm just checking. I don't see any more questions, and we're at the hour. So maybe if you have any more questions, I'll invite you to send an email to Monica. We'll have her contact information on our website as usual. And okay, I think we can wrap this up. The presentation will be available.
Thank you all very much. It was really a pleasure to be able to tell you about this work.
Thank you. Thank you so much, Dr. Valluri, and thank you everyone for attending. So this presentation will be available on our website and on Linea's YouTube channel. Everyone have a great day, stay safe, and I hope to see you all again in our next webinar.
Okay. Thank you very much, everybody.
Thank you very much.